Did you know that manipulating light at the nanoscale can lead to remarkable innovations in technology and medicine? This is the essence of nanophotonics. But before we explore this fascinating field, let's take a step back and understand two fundamental concepts: photonics and nanotechnology. Photonics is the science of light. It deals with the basic principles of light, including how it's generated, transmitted, detected, and manipulated. This field of study extends beyond the visible spectrum, encompassing all forms of radiant energy from gamma rays to radio waves. It's a cornerstone of modern science and engineering, playing a pivotal role in innovations ranging from laser surgery to fiber optic communications. On the other hand, we have nanotechnology. This scientific domain deals with the manipulation and control of matter at the nanoscale, typically between 1 and 100 nanometers. To put this into perspective, a single sheet of paper is about 100,000 nanometers thick. Nanotechnology has revolutionized countless areas of science and engineering, enabling us to build structures and devices at the molecular level. This has led to breakthroughs in fields as diverse as medicine, electronics, and energy production. Now imagine the possibilities when we merge these two fields. That's exactly what nanophotonics does. It's a multidisciplinary field that explores how light interacts with nanostructures. It combines the principles of photonics and nanotechnology to manipulate light at the nanoscale. The result? A world of opportunities for new technologies and applications. Nanophotonics is like a bridge, connecting the macroscopic world of light with the microscopic world of atoms and molecules. It's a bridge that could lead us to faster computers, more efficient solar cells, and even new ways to diagnose and treat disease. To understand nanophotonics, we first need to grasp the principles of photonics and nanotechnology. So let's embark on this journey into the world of light and atoms and discover the wonders of nanophotonics together. Nanophotonics operates at the intersection of quantum mechanics and light-matter interaction. This fascinating scientific field bridges the quantum world with that of photonics, allowing us to manipulate light at the nanoscale. To fully grasp its core principles, we need to understand some essential concepts of quantum mechanics and know how light interacts with nanostructures. Let's start with quantum mechanics. In the realm of the very small, particles behave differently than in our everyday world. Two essential quantum mechanics concepts related to nanophotonics are quantum dots and quantum wells. Quantum dots are tiny particles so small that they are often called artificial atoms. They have the unique property of confining electrons in 3 dimensions, leading to fascinating optical and electronic phenomena. Quantum wells, on the other hand, confine electrons in 2 dimensions. These structures allow for precise control over electron behavior, which is crucial for the development of nanophotonic devices. Moving on, let's talk about how light interacts with matter at the nanoscale. When photons encounter nanostructures, they can cause electrons to oscillate, leading to phenomena like quantum confinement and surface plasmon resonance. Quantum confinement refers to the effect where the electronic and optical properties of a material change as its size shrinks to the nanoscale. Surface plasmon resonance, meanwhile, is a resonance phenomenon that amplifies the interaction between light and electrons on a metal surface. Both phenomena are crucial in the design and operation of nanophotonic devices. Finally, we'll introduce photonic crystals and waveguides. Photonic crystals are materials with a periodic variation in refractive index, creating what's known as a photonic bandgap. This bandgap can be manipulated to control and guide the flow of light. Waveguides, as their name suggests, are structures designed to guide light waves from one point to another. At the nanoscale, these waveguides can be engineered to control light with unprecedented precision. With these basic principles, we can now explore how to create and analyze nanophotonic structures. By understanding these fundamental principles of nanophotonics, we're well on our way to unlocking the potential of this exciting field. The construction and examination of nanostructures require precise techniques. To construct these incredibly tiny structures, we use nanofabrication methods, which we can categorize into the top-down approach and the bottom-up approach. Top-down fabrication is like sculpting a marble statue, where you start with a large block and chip away until you have your desired shape. Lithography, a common top-down method, uses light or electrons to etch patterns into a material. This method is well established in the semiconductor industry and has been instrumental in the miniaturization of electronic devices. On the other hand, the bottom-up approach is more like building with Lego blocks. You start with small components and assemble them into larger structures. Self-assembly, a bottom-up method, involves designing materials so that their natural interactions guide them to form the desired structure. This method can create complex nanostructures with less energy and potentially higher precision than top-down methods. However, once we have our nanostructures, we need to examine them to ensure they have the right properties. That's where characterization techniques come in. Scanning electron microscopy, or SEM, bombards the sample with electrons and creates an image based on the electrons that bounce back. This gives us detailed information about the surface topology and composition. Transmission electron microscopy, or TEM, is similar to SEM, but the electrons pass through the sample, providing an even more detailed image and allowing us to see the internal structure of our nanostructures. Atomic force microscopy, or AFM, uses a tiny probe to trace the surface of the sample, creating a map of its topography at the atomic level. Finally, spectroscopy methods involve shining light on the sample and analyzing the light that's absorbed, emitted, or scattered. This can reveal a wealth of information about the sample's structure and composition. With these methods, we can fabricate and analyze nanophotonic structures to build innovative devices. With such knowledge, we can continue to push the boundaries of what's possible in the realm of nanophotonics. Nanophotonics has the potential to revolutionize various fields, from information technology to medicine. This statement is more than just a prediction. It's a glimpse into the transformative power of this groundbreaking science. Let's begin by exploring nanophotonic devices. You're already familiar with LEDs, lasers, photodetectors, and solar cells, but nanophotonics takes these to a whole new level. By manipulating light at the nanoscale, we can create devices that are more efficient, compact, and versatile than their macro-scale counterparts. For example, nanophotonic LEDs can emit brighter light with less energy, while nanoscale lasers can be made incredibly small, yet still powerful. Photodetectors, essential for sensing light, can be made more sensitive, and solar cells can absorb more sunlight and convert it into electricity more efficiently than ever before. These enhancements arise from the unique properties of materials and light at the nanoscale, showcasing the exciting potential of nanophotonic device design. Now let's talk about information technology, a field that's all about data, storing it, processing it, and transmitting it. Nanophotonics can help improve all these aspects. For instance, in data storage, nanophotonic structures can be used to create ultra-dense memory devices, effectively storing more data in less space. In terms of data processing, nanophotonic circuits can perform computations using light instead of electricity, leading to faster and more energy-efficient processing. And when it comes to data transmission, nanophotonic cables can carry more information over longer distances with less loss than traditional cables. This can open the door to optical computing, a paradigm shift that could lead to computers performing operations at the speed of light. Lastly, let's consider the field of medicine, where nanophotonics is starting to make significant strides. This is especially evident in the subfield of biophotonics, which involves the use of light for medical diagnostics, imaging, and therapy. Nanophotonics can enhance these areas by providing more precise and detailed information. For instance, nanoparticle-based drug delivery systems can be tracked and controlled using light, enabling targeted treatment of diseases. Similarly, biosensors can be enhanced with nanophotonics to detect minute changes in biological systems, providing early diagnosis of diseases. Furthermore, nanophotonic devices can be used for high-resolution imaging and advanced therapeutic techniques, offering new ways to understand and treat various medical conditions. These are just a few examples of how nanophotonics is being applied today. From creating more efficient devices to revolutionizing data handling to enhancing medical techniques, nanophotonics is truly a game changer. And remember, we're still in the early stages of this exciting field. These applications only scratch the surface of what is possible with nanophotonics. As scientists continue to explore and innovate, who knows what amazing advancements the future of nanophotonics will bring. Nanophotonics is not just about shrinking photonics to the nanoscale. It involves numerous advanced and exciting topics. Let's start with nonlinear nanophotonics. This field explores how light behaves in nanostructures when the response is not directly proportional to the input light intensity. In other words, the light-matter interactions become more complex and intriguing as we venture into the realm of the very small. This nonlinearity opens up a range of applications, including all optical data processing and the creation of ultra-compact light sources. Moving on, we find ourselves in the world of metamaterials and metasurfaces. These are materials engineered to have properties that do not occur naturally. By carefully designing their nanostructure, we can manipulate how these materials interact with light, leading to applications like superlenses that surpass traditional limits of resolution, or cloaking devices that could render objects invisible to certain frequencies of light. Next up, we have quantum nanophotonics. This field marries the principles of quantum mechanics with nanophotonics, leading to exciting developments in quantum communication and quantum computing. Quantum nanophotonics could be a game changer, allowing us to transmit information in a way that is fundamentally secure and to perform computations at speeds that are currently unimaginable. Let's not forget plasmonic nanoantennas. These tiny devices convert light into plasmons, oscillations of electrons that can be confined to much smaller volumes than light itself. This enables us to control and manipulate light at scales far below its wavelength, opening up possibilities in fields such as nanoscale imaging and high-density data storage. The role of two-dimensional materials in nanophotonics is a topic that's been gaining significant attention. Materials like graphene and transition metal dichalcogenides, which are just an atom or two thick, have unique optical properties that make them extremely useful in nanophotonic devices. They could help us to create devices that are smaller, faster, and more efficient than ever before. Finally, we come to spintronics with photonic nanostructures. Spintronics, or spin electronics, involves the use of the spin of electrons, in addition to their charge, for information processing. When combined with photonic nanostructures, this could lead to the development of devices that are not only ultra-compact and fast, but also have lower power consumption, since spin can be manipulated with minimal energy input. These advanced topics demonstrate the vast potential and the exciting future of nanophotonics. The future of nanophotonics is bright, with endless possibilities for scientific and technological advancements. As we peer into the future, we may very well be looking through a lens crafted by nanophotonics. This dynamic field, which merges the realms of light and nanotechnology, is on the cusp of revolutionizing our world in ways we are only beginning to comprehend. Consider the realm of data storage and processing. Today's digital world demands faster, more efficient ways to handle vast amounts of information. Nanophotonic devices manipulating light at the nanoscale have the potential to outpace current electronic systems, paving the way for ultra-fast, light-based computing. In healthcare, nanophotonics could redefine diagnostics and treatment. Imagine nanoparticles that can target and treat cancer cells with precision, or biosensors that can detect diseases at their earliest stages. These are not mere fantasies, but real possibilities being explored in the field of biophotonics. Energy is yet another area where nanophotonics could shine. From improving the efficiency of solar cells to developing new forms of light-based energy storage, the potential is immense. Nanophotonic materials could help us harness the power of light more effectively, contributing to a more sustainable future. And let's not forget about communication. The integration of quantum information science with nanophotonics could lead to quantum communication systems, offering unprecedented levels of security and speed. Quantum cryptography, powered by nanophotonics, could very well be the future of secure communications. But the journey of exploration doesn't stop there. Researchers are pushing the boundaries of nanophotonics into new territories. Nonlinear optical effects in nanostructures, engineered metamaterials, photonic crystal fibers, and two-dimensional nanomaterials are all areas ripe for discovery and innovation. However, the path ahead is not without its challenges. Nanofabrication techniques must continue to evolve to keep pace with the complex demands of nanophotonic applications. And as with any technological advancement, we must consider the environmental and health impacts of these nanomaterials. Yet, the potential rewards are worth the effort. The fusion of light and nanotechnology opens up a world of possibilities, from the microscopic to the grand scale. It's a world where we can manipulate light to heal, to communicate, to compute, and to power our lives. The future of nanophotonics is not just about new gadgets or technologies. It's about reimagining the way we understand and interact with the world around us. It's about taking the fundamental properties of light and nanomaterials and using them to solve real-world challenges. So, as we wrap up, let's remember that nanophotonics is more than a scientific discipline. It's a vision of a future where light, at the tiniest scales, can have a big impact on our lives. From healthcare to computing, from energy to communication, the potential of nanophotonics is vast and varied. Nanophotonics, with its ability to manipulate light at the nanoscale, holds the key to many future technological and scientific breakthroughs.